So in this particular section, we are going to discuss electric potential energy. So basically what we'll do is, we'll consider a system comprising of many point static charges. So in such a scenario, how to define the potential energy, electric potential energy of that particular system. So let's first understand its definition and then we will try to obtain the expression for a system comprising of 2-point charges, 3-point charges, and then we can generalize to a system comprising of n-point charges, right? So let's first concentrate upon its definition. So let us consider this to be a system comprising of point and static charges. This is Q1, Q2, Q3, Q4, Qi and Qnth. These are the charges which constitutes this system. Now, initially we'll consider all these charges to be located at infinity. Suppose all these charges are initially assumed to be located at infinity. All these charges are assumed to be located at infinity. Now, some amount of work will be done in bringing all those charges from infinity to their respective locations. Suppose some work is done in bringing Q1 from infinity to this point. Again, in bringing Q2 from infinity to this point. So, some finite amount of work will definitely be required to bring the charges constituting the system from infinity to their respective positions. And as per work energy theorem, this amount of work done gets stored in the system in the form of its potential energy. So, electric potential energy of a system comprising of any number of charges may be defined as the total amount of work that is required to be done in bringing those charges constituting the system from infinity to their respective positions. So, that's the definition of electric potential energy. Now, let's find its expression. So, we will find the expression for the potential energy for a system comprising of 2-point static charges. 2-point static charges. For this, what we consider is, again, we will consider this to be a system. A and B are the respective positions of Q1 and Q2. Let these 2-point static charges be separated by R12, and this is suppose air or vacuum, right? Now, in order to understand the concept, what you imagine is, initially we will imagine these 2-point static charges to be located at infinity. Suppose this is infinity, this is where the two charges are located. Because we need to get the total amount of work done in bringing these two charges from infinity to their respective positions A and B. And that total amount of work done will give us the potential energy of this particular system. So that should be our approach. So let's first talk about W1, which is the work done in bringing charge Q1 from infinity to its respective position A. Now look, as we bring charge Q1 from infinity to its respective position A, there is no other charge present near its vicinity. So it won't experience any electric force. It is not under the influence of any electric field. So, work done in bringing the charge Q1 from infinity to its respective position A in the absence of any other charge or in the absence of any other electric field would be 0. No amount of work is to be done. So, it is 0. Since there is no other charge present near its vicinity, it won't exert any force. Therefore, in the absence of any force, work done would be 0. Right? Now, Q1. So, in order to bring charge Q1 from infinity to its respective position A, no amount of work is to be done. Right? Now, second step is, we'll bring charge Q2 from infinity to its respective position B. This is Q2. Now, when we are bringing charge Q2 from infinity to point B, already charge Q1 is present at point A. So, Q2 is to be brought from infinity to point B under the influence of charge Q1. So, it will set up its own electric field. Due to this charge, there will be some potential. So, W2 is the work done in bringing charge Q2 from infinity to point B. Formula for the work done is potential multiplied by charge. Now you need to recall this formula. The potential at point B would be equal to work done per unit charge, the charge which is to be moved from infinity to that particular point. So this we are considering to be W2. So work done in bringing charge Q2 from infinity to its respective position B under the influence of Q1 would be equal to potential at point B. This is due to charge Q1 multiplied by this Q2. Right? So let's substitute the expression for the potential. Potential at a point due to a charge is KQ by R, isn't it? So at point B, the potential due to charge Q1, it will be 1 over 4 pi epsilon naught Q1, this is the charge. And distance of this observation point B from point A is R1 multiplied by Q2. Q2 is the charge that is to be moved from infinity to its respective position B. So put this as equation 2. So as per the definition, total electric potential energy of the system comprising of these 2 point static charges is given by W1 plus W2. So we can very well substitute the value W1 and W2 from equation 1 and 2. So W1 is 0, substitute the value of W2 we get 1 over 4 pi epsilon naught Q1 Q2 divided by R1. This is the expression for the potential energy of a system comprising of 2 point static charges. And as you are aware, potential energy is a scalar quantity. It will have only magnitude but no direction. So you can extend the same concept while deriving the expression for 3 point static charges. So let's do it. So in order to derive the expression for 3 point static charges, what we will do is we'll consider a system comprising of 3 charges, say Q1, Q2 and Q3. These are the 3 charges A, B, C, located at A, B, C respectively. Now suppose the separation between AB, it can be considered to be R12, between BC, it can be considered to be R23, and between Q1 and Q3, that is AC, the distance can be considered to be R13, right? So, in order to find out the expression for the potential energy, again we will make use of the same concept. We will imagine initially all these 3, Q1, Q2, Q3 point static charges to be placed at infinity. Suppose this is the infinity and this is where all the 3 charges are placed. All the 3 charges, Q1, Q2, Q3, they are placed. They are placed at infinity, right? They are placed at infinity. Now, as we have discussed earlier, work done in bringing charge Q1 from infinity to its respective position, point A, in the absence of any other charges around its vicinity, would be 0. Because in the absence of any other charges, it won't experience any electric force. So in the absence of any force, work done is 0. So always remember, in order to bring the first charge from infinity to its respective location in the absence of any other charges, no amount of work is required to be done. So this is the first step, right? Now Q1 is already there at point A. Now work done in bringing charge Q2 from infinity to its respective location B. Now Q1 is already present over here. So it needs to be brought to its position B under the influence of electric field due to this charge Q1. Q1 will act as a source charge, isn't it? So in such a scenario, work done is given by potential at point B due to charge Q1 multiplied by the charge that is to be moved from infinity to that particular point, that is Q2. So potential at point B due to charge Q1 would be 1 over 4 pi epsilon Q1 by R12. This is the distance multiplied by Q2. So this is the expression, right? So we have found the expression for the work done in bringing charges Q1 and Q2 from infinity to their respective positions A and B. Now what to do is, let's find out the work done in bringing charge Q3 from infinity to its respective position C. Now, as we are bringing charge Q3 from infinity to point C, already the charges Q1 and Q2 are already present at points A and B. So here at point C, the net potential would be due to charge Q1 as well as Q2. So, work done in bringing charge Q3 from infinity to point C. It will be equal to, again we will make use of the same expression, potential at point C, it is given by work done per unit charge in bringing that charge from infinity to that particular point. So work done would be potential at that point multiplied by the charge. So it will be potential at point C due to Q1 and Q2 multiplied by charge Q3. So we can substitute the value. You are aware potential is a scalar quantity. So the net potential at point C due to these two charges would be 1 over 4 pi epsilon Q1 divided by the distance of point C from A, that is charge Q1 is R13. 1 over 4 pi epsilon, the potential at point C due to charge Q2 would be R23 multiplied by Q3. So this is equation 3. So as we have discussed, as per the definition, total amount of work that is required to be done in bringing the charges constituting the system from infinity to their respective location, that is potential energy of the system. So by definition, potential energy in this case would be W1 plus W2 plus W3. So substitute the value of W1, W2 and W3 from 1, 2 and 3. What we get is, look, 1 over 4 pi epsilon, it is common. Q1, Q2 divided by R12 plus, look, Q1, Q3 divided by R13. This represents the distance between these two charges under conservation, right? And this term, we have already taken 1 over 4 pi epsilon as common. So Q2, Q3 divided by R23. So this is the expression for the potential energy of a system comprising of 3-point charges. Similarly, we can extend the same concept for a system comprising of n-point charges. So let's see how the expression will get changed in case we consider a system comprising of n-point charges or n-point charges. So we'll generalize this expression. So let's generalize for a system comprising of n-point static charges. The expression for the potential energy would be summation I equals to 1, j equals to 1 to n. N is the number of point static charges. And here, this is I, this is j. I won't be equal to j. If I is equal to 1, j will take some other value except 1. If I is equal to 2, j can take any value except 2 till n. Qi, qj divided by rij. So this will be this term. And then 1 over 4 pi epsilon. Now look, this is it. If we expand by using this particular expression for 2-point static charges, the value of n would be 2. For 3-point static charges, the value of n would be 3. So if we expand, you will notice every term will get repeated. Every term is written twice. Q12 over R12, Q2 Q1 into R21. So it represents the same thing. So in order to compensate that repeated term, the factor of this half is introduced over here. So this is a very, very important thing. The factor half is introduced so as to compensate on that repeated terms. Each term gets repeated. It gets repeated twice so as to compensate that this numerical factor half is to be introduced. You can easily justify this expression. For example, for n equals to 2, what to do is, when I equals to 1, j would be equal to 2. When I equals to 2, then j would be equal to 1, isn't it? These are the combinations. I can't be equal to j. So if you expand using this expression, what do you get? Half 1 over 4 pi epsilon naught, and then let's expand it. This term, let's consider this term. Q1, Q2 divided by R12 plus summation, addition of. Then consider this term. Q2, Q1 divided by R21. It's a scalar. So both these terms represent the same thing. So what you get is 1 over 4 pi epsilon twice Q1, Q2 divided by R12. So this 2 and this half get cancelled. So we are left with 1 over 4 pi epsilon Q1, Q2 divided by R12. This is the expression for the potential energy of a system comprising of 2 point static charges. Similarly, for n equals to 3, you can easily justify. There will be 6 terms, each term getting repeated twice. So this numerical factor half will compensate on that, and you will get the expression, you will get the required expression, right? Another, I'll give you a very important and simple tip to remember the formula. So what to do is, how to remember this formula when solving question, how to obtain the appropriate expression and to apply the appropriate formula. Look, for n equals to 2, this is just for ready reference. In order to remember the formula, I am giving you a simple illustration. These are the two charges. The combination can be only 1, 2. This is the only way they can get connected. So this is the term which is common, 1 over 4 pi epsilon. Okay. Q1, Q2 divided by the separation between them. This is it. This will be the expression for n equals to 2. For n equals to 3, these are the 3 charges. What are the combination? 1, 2, 1, 3, 2, 3. These are the 3 possible combinations. So in this case, the potential energy would be 1 over 4 pi epsilon. Look, these two terms, we'll consider Q1, Q2 divided by the separation between them, that is R12. Then we can consider 1, 3. So it will be Q1, Q3 divided by R13 plus these are the two terms left, that is Q2, Q3 divided by R23. So this is how you can derive the formula. For n equals to 4, these are the charges 1, 2, 3, 4. What will be the combination or what are the number of terms? 1, 2, 1, 3, 1, 4. 2, 3, 2, 4. And lastly 3, 4. So there will be 6 terms. So in such a case, the expression for the potential energy would be 1 over 4 pi epsilon. Look, 1, 2, Q1, Q2 over R12, 1, 3, Q1, Q3 over R13, 1, 4, Q1, Q4 divided by R14 plus 2, 3, 2, 4, that is Q2, Q3 divided by R23 plus Q2, Q4 divided by R24 and lastly 3, 4, Q3, Q4 divided by R34. So this is the expression for the potential energy of a system comprising of 4 point static charges. So this is a very, very simple illustration. You can easily remember this formula, right? So this is regarding the electric potential energy.